Now, let's calculate the pH for the weak acid and the weak base. Remember that weak acid and weak base are partially dissociated in aqueous solutions. That means the concentration of the H plus or the OH- ions that obtained from the dissociation must be less than the concentration of its weak acid or weak base that has been introduced. So, solving the X value in the dissociation of the weak acid and the weak base is a bit different from the strong acid and the strong base. We can use two methods to determine the value of X in weak acid and the weak base dissociation. First, if the value of Ka or Kb is larger than exponent -5, thus we can use the quadratic equation method. Using this method, we just use the calculator. To get the value of X. The second method, if the value of Ka or Kb is equal or smaller than exponent -5. So if the Ka Kb is smaller or equals to exponent -5, thus we can use the approximation method, which means this is involving the assumption. Now, let's take a look for the first example in solving the X value for the weak acid dissociation. This is the questions. Calculate the pH of 0.10 molar of acetic acid solution with given Ka 1.8 exponent -5. By using ice table, insert the initial values that given in the questions, that is, initial concentration of the acetic acid solutions. The initial concentration given is 0.10 molar. So, in this reaction, the dissociation of the weak acid involves the dissociation in water. But remember that water is a pure liquid. So, the pure liquid has a constant concentration. Therefore, the concentration of H2O do not count in the expressions. So initially, the product is not formed yet, therefore they have a zero concentration. During the reaction, there must have changes in the concentration of the reactant and product. The reactant will decrease in concentration, the product will increase in the concentration. The reactant, which is involved the acetic acid, they have decreased in concentration. So to indicate the decrease in concentration, we use the negative sign. How much it has been decreased? Since this is a weak acid, they are partially dissociate. Therefore, we cannot determine the exact value of dissociation. So, we assume the dissociation is equals to X. Remember, the value of X must be accordingly to its stoichiometric coefficient, which means 1 mole of ethanoic acid equals to 1x. For the product, during the reaction, they have increased in concentration. Same as the acetic acid dissociated, the amount of product formed is unknown. So, we can use X as an assumption value. As well as the H3O+, they are also increased in concentration with plus X. At the end of the reaction, we can determine the final concentration that remaining after the reaction. That is 0.10 molar initial concentration of the acetic acid minus the changes of concentration, which is equals to X. Water is not count in the reaction, but for the ions CH3CO minus, that is 0 plus X equals to X. H3O plus 0 plus X, which is also equals to X. So this is what we have at the end of the reactions. So how to solve the value of X? We can solve the value of X by expressing the dissociation constant K. The dissociation constant K for the acid is Ka. Writing the Ka expression involving for both of the reactant and the product. That is, the concentration of the product divided by its concentration of the reactant. The concentration of the product here is concentration of CH3COO minus ions and H3O plus ion. Remember, there must be accordingly to its stoichiometric coefficient. So in this reaction, there are only 1 mole of CH3CO minus and 1 mole of H3O plus ions. Therefore, they are power of 1 and power of 1. Divide by its reactant. So the reactant that can be counted in the expression is only involve the aqueous of acetic acid. Therefore, concentration CH3 COOH concentration to the power of 1. So, since the Ka is the equilibrium constant, so the value that need to be substituted into the expression must be the equilibrium value. So, equilibrium value, we can refer to the ice table, which represent by the third row of the table. So, the concentration of the CH3CO minus according to the ice table, that is equals to X. The concentration of the H3O plus ions at equilibrium is also equals to X. Divide by the concentration of its acid at equilibrium, that is equals to 0.10 minus X. The value of Ka is already given, that is equals to 1.8 exponent negative 5. So this is what we call the acid dissociation constant expression. Now, how to determine the value of X? From the expression, we have obtained that the Ka is equals to X divided by 0.1 minus X. That is equals to 1.8 exponent negative 5. So, since the value of Ka is equals to exponent negative 5, therefore we can assume this value is very small. So since the Ka is very small, or the dissociation is very small, thus we can use the assumption method or the approximation method. That means we assume that the Ka is very small, thus assume that the dissociation of X is very small. So we can determine from the dissociation of the acid of 0.10 molar minus X is very small dissociated, so we can neglect the value of X with 0.10 molar only. Therefore, we can rewrite the equation of Ka is equals to X squared divided by 0.10 only, whereas the X value, which is amount dissociated from the acid, is neglected since it is very small. So the value is 1.8 exponent negative 5 for the Ka. Now we can solve the value of X by using the calculator. So determine the value of X, that is 1.8 exponent negative 5 multiply with 0.10 and square root. So we get the value of X equals to 1.34 exponent negative 3 molar. So from the ice table, the value of X at equilibrium is equivalent to the concentration of the H3O plus. So now we have a concentration of H3O plus. So to determine the pH, we need the concentration of the H plus or the H3O plus. So now we can use the concentration to determine the pH of the solution. That is, pH equals to negative log H3O plus concentrations. Substitute the value, negative log of 1.34 exponent negative 3, that is equals to 2.87. So that is the pH value for the acetic acid. Now, let's try one more example to calculate the pH of a weak acid. So the question is, calculate the pH of 0.036 molar of the nitrous acid solutions. We were given Ka 4.5 exponent negative 4. So first, draw the ice table and write the balanced chemical equations. So the initial concentration of the acid given is 0.036 molar. Water with a constant concentration, so it is not count in the expression. The product is not produced yet, so we have a 0 concentration for the product. When the reaction occurs, so we have a changes to the concentration of the reactant as well as the product, whereas the reactant will decrease in concentration, the product will increase in concentration. So to indicate the increase and the decrease in concentration, we use the minus and positive sign. So the minus is referred to the decrease in concentration. So since the reactant is decreased in concentration, so we can assume the changes of the reactant, which is referred to the nitrous acid, is minus concentration. So how much it decreased in concentration? So since the weak acid is partially dissociates, so we can assume the value of partially dissociate as X, which is the unknown. So HNO2 of nitrous acid is dissociate as much as X, as well as the NO2 minus and H3O plus ions. They are produced during the reaction, so we use the positive sign as much as how the nitrous acid dissociates, which is equals to X. And also H3O plus with positive X. So remember, the quantities of the X is accordingly to its stoichiometric coefficient. So from these balance equations, so we can see that is involving only 1 mole of nitrous acid, 1 mole of NO2 minus, and 1 mole of H3O plus ions. Therefore, they are only involving 1 X of unknown value. So now we can determine the value of the concentration after the reaction, or the equilibrium concentration. The equilibrium concentration for the nitrous acid at the end of the reaction remaining is 0.036 molar of its initial dissociate of X. H2O is not count in the dissociation. NO2 minus is 0 plus X, H3O plus 0 plus X equals to X. So now we have the values of equilibrium concentration for all the substance involved in the dissociations. That is HNO2 concentration at equilibrium is equals to 0.036 minus X. NO2 minus at equilibrium is obtained X concentration, as well as the H3O plus with X concentration. Therefore, we can express the dissociation constant for the acid is Ka equals to concentration of the product, which is NO2 minus ions with H3O plus ions, divided by the acid of HNO2 concentration. Substituting the equilibrium value, that is equals to NO2 minus equals to X, H3O plus is equals to X, divided by HNO2 equals to 0.036 minus X. So remember that Ka means acid dissociation constant at equilibrium. So that means the value that has been substituted into the expression is only equilibrium value. So the Ka value is given 4.5 exponent negative 4. So that's it, the expression of the Ka for this reaction. Now, how can we determine the value of X so that we can determine the pH for this solution? Since the Ka expression is equals to X squared divided by 0.036 molar minus X, which is equals to the Ka value given 4.5 exponent negative 4. So we can determine the value of X by using two methods, either the approximation method or the quadratic method. So since the Ka value given with a value of exponent negative 4, so exponent negative 4 is larger than exponent negative 5. So when the value is larger than exponent negative 5, so we have to use the quadratic method. Okay, quadratic method to solve X. Alright, so how to solving the X using the quadratic method? So using the quadratic method, you can calculate or determine the value of X using your calculator. So let's write the equation of the quadratic. When the x squared divided by 0.0 x squared divided by 0.036 minus x, that is equals to 4.5 exponent negative 4. So the quadratic obtain the x squared plus 4.5 exponent negative 4 minus 1.62 exponent negative 5 equals to. Now you can use 4.5x. Now you can use your calculator by using the equation formula to solving the value of x. So use your calculator, choose the equations with 2 degree. So 1 so we will obtain 2 value of x equals to 3.80 exponent negative 3, and the second x is negative 4.26 exponent negative 3. So we have 2 value of x, one with positive value, one with negative value. So definitely we will use the positive value as the valid value. So the negative is the invalid value. So to proceed in calculating the pH of this solution, we will use the valid value of x. Now, how to determine the concentration as well as the pH? So since the value of x obtained is 3.8 exponent negative 3 molar, which is from the value of x. So from the ICE table, x refer to the concentrations of the H3O plus at equilibrium, which means we have obtained the concentration of the H3O plus. Then we can determine the pH by using the formula of negative log of H3O plus concentrations. Substitute the values, that is negative log 3.8 exponent negative 3 molar, that is equals to negative log 3.8 that is equals to 2.42 of the pH. Alright, so that's it. Now, how to solve the value of x in the weak-base dissociation constant. The example of question is calculate the concentration of the OH- ions, the pH, and the percent of the dissociation if initial concentration of ammonia is 0.15 molar. The value of Kb is given with 1.8 exponent negative 5. So now we can use the ice table to determine the equilibrium concentration. The initial concentration of the ammonia is 0.15 molar. The dissociation of ammonia in water will give ammonium ion NH4 plus and hydroxide ion OH minus. You have to write the balanced chemical equation in the ice table. So since in the equation H2O is a pure liquid, so it is not involved in the expression due to the constant concentration. So for the ammonium ion and the hydroxide ion, initially it is 0 concentration. But when the reaction occurs, so they have a changes in the concentration of the reactant and the product. The reactant will decrease in concentration. So we use the negative sign to indicate the decrease in concentration. So how much it decrease in concentration? So since the ammonia is the weak acid, a weak base, thus it is partially dissociates. So the value of partially dissociate is unknown. Therefore, we can assume that the quantities that dissociate with X. As well as the product form, which is ammonium form of X concentration, as well as the OH minus with X concentration. So make sure that the X value for the changes must be accordingly to its stoichiometric coefficients. So at the end of the reactions, the reaction achieved the equilibrium concentration. Thus, for the ammonia, initially introduced 0.15 molar. So after the reaction, they have dissociate about X concentration. Therefore, finally, the remaining is obtained from 0.15 minus X. For the water is do not count. For the ammonium ion, 0 plus X. For the hydroxide is 0 plus X. So now we have equilibrium concentration for each of the substances that involved in the dissociation. Then we can express the dissociation constant. So remember that is ammonia is a weak base, so that represents Kb. That means the dissociation constant for the base. Kb expression is concentration of the product over divided by concentration of the reactant. So the product here in the dissociation is the ammonium ion NH4 plus and the hydroxide ion OH minus divided by the concentration of it with base ammonia. Remember that must be accordingly to its stoichiometric coefficient. So in this reaction, they are all 1 mole of a substance. So then substitute the value that obtained from the ice table. The ammonium ion obtained at equilibrium is equals to X. The hydroxide ion obtained at equilibrium is also X, while the ammonia obtained at equilibrium is 0.15 minus X. So the value of Ka is already, the value of Kb is already given with 1.8 exponent negative 5. So now we need to solve the value of X using the Kb expression. Since from the Kb expression, we have X squared divide by 0.15 minus x, that is equals to 1.8 exponent negative 5. So since the value of Kb is exponent negative 5, so we can assume this value is very small. Thus, we will use the assumption or the approximation method. So, write the explanation. Since the Kb value is very small, thus we can assume that x of dissociated quantities is very small. Therefore, 0.15 minus x, since x is very small, so we can neglect the value of x, that is equals to 0.15 only. So rewrite the Kb expression. Kb that equals to x squared divided by 0.15 only, since the x has been neglected due to the assumptions. That is equals 1.8 exponent negative 5. Now, you can solve the x by calculating using the calculator. So, x obtained is equals to 1.8 exponent negative 5 multiply with 0.15 and square root, then you get 1.64 exponent negative 3 molar. From the ice table, the x at equilibrium is referred to the concentrations of the OH minus. So now we have the concentration of the OH minus. So how can we determine the value of the pH from the concentration of the OH minus? We can use the concentration of OH minus to determine the pOH. That is negative log equals to concentration of OH minus. Substitute the values of concentration. Negative log 1.64 exponent negative 3, that is equals to 2.78 of pOH. To determine the pH, we just minus from 14 minus pOH. So we get 14 minus 2.78 equals to 11.22. Alright, so this is the pH obtained. So we have another step to determine the pH, or another method, whereas we can use the water dissociation. That is, okay, the alternative answer to determine the pH or the concentration of the H plus using the Kw, which is concentration of H3O plus equivalence to times concentration of OH minus equals to 1 exponent negative 14. So since the concentration of OH minus is known as 1.64, so we can determine the H3O plus concentration with 1.0 exponent negative 14 divided by concentration of OH minus, that is 1.0 exponent negative 14 divided by 1.64 exponent negative 3. That is equals to 6.09 exponent negative 12. So pH is equals to negative log of 6.09 exponent negative 12, that is equals to 11.22. So we have two methods to determine the pH. Now we can determine the percentage of dissociation of ammonia. That is equals to quantities or the molarities that has been dissociated divided by its initial amount or the initial concentrations. Times 100. So from the ICE table, we have assumed that amount dissociated in the reactions of dissociation of ammonia is equals to X. So the quantities is represented by X divided by its initial concentration. So let's use C times 100. Substitute the value from the ICE table. We have found out that the X value is equals to 1.64 exponent negative 3, dissociated from its initial concentration given, that is 0.15 molar, times 100. That will obtain the percentage of dissociation equals to 1.09%. So that's the end of the videos. So you can try more questions from the exercises and the tutorial questions.